Back in December, California scientists made a major breakthrough, a nuclear fusion reaction that produced more energy than was used to create it. Well, scientists have done it again, and this time their results produced even more energy. Joining us now to discuss the implications.
Wait a minute. Before we go further into today's topic, let me introduce myself. Greetings. Guys, the name, and today, I will be presenting on the topic, fusion confinement, magnetic for SFT4063 fusion energy. Let's go! Many of us have heard the terms nuclear fission and nuclear fusion. Nuclear fusion and fission produce a massive amount of energy. Nuclear fission is a reaction in which heavy elements diffuse and form lighter elements. Nuclear fusion is a reaction through which two or more light nuclei collide to form a heavier nucleus. The nuclear fusion process occurs in elements that have a low atomic number, such as hydrogen. For example, when deuterium and tritium fuse together, their components are recombined to form a helium atom and a fast neutron. As the two heavy isotopes are recombined into a helium atom and a neutron, the leftover extra mass is transformed into kinetic energy. The participating nuclei should be brought together for the nuclear fusion reaction to occur. They should be brought so close to each other that the nuclear forces become active and glue to the nuclei together. Every star in the universe, including the Sun, is alive due to nuclear fusion. It is through this process that they produce an enormous amount of heat and energy. The pressure at the core of any star is tremendously high, and that is where the nuclear fusion reaction occurs. For example, the temperature at the Sun's core is around 15 million degrees Celsius. At this temperature, coupled with very high pressure, two isotopes of hydrogen, deuterium and tritium, fuse to form helium and release a massive amount of energy in the form of heat. Around 600 million tons of hydrogen are converted into helium every second in the Sun. The reactions which take place in the Sun provide an example of nuclear fusion. For many years, scientists have tried to recreate nuclear fusion on Earth. Why? It could provide humans with a clean source of energy. It produces a minimal amount of nuclear waste as compared to fission reactions. This could help lower carbon emissions and the levels of other greenhouse gases in the atmosphere. In addition, the fuel for fusion, deuterium, and tritium, are also readily available in nature. That possibility has led some scientists to the idea of creating an artificial sun. What do we mean by artificial sun? Are people creating giant balls of gas that can heat planets far from the center of our solar system? Of course not. Or, at least, not yet. Instead, the artificial suns being created today are nuclear fusion reactors. And that's a bit of a trailer on our topic for today. Magnetic confinement, the Earth's artificial sun. Magnetic confinement is a technique used in the field of nuclear fusion research to control and contain hot plasma, which is the fuel for nuclear fusion reactions. The goal of magnetic confinement is to create and maintain the conditions necessary for sustained nuclear fusion, where light atomic nuclei combine to release energy. In plasma, electrons are stripped from the atoms. An atom with no electrons orbiting around the nucleus is said to be ionized and is called an ion. As a result, plasma is made of ions and free electrons. In this state, scientists can stimulate ions so that they smash into one another, fuse and release energy. Keeping plasmas stable in order to extract energy is difficult. They are chaotic, superhot, and prone to turbulence and other instabilities. Understanding, modeling, and controlling plasma is extremely complex, but researchers have made great strides over the past decades. For that, scientists come up with magnetic confinement devices to manipulate plasmas. We will go through two magnetic confinement devices, tokamak and stellarator. Tokamaks are the most widely researched and developed magnetic confinement devices. The name tokamak is derived from the Russian words for toroidal chamber with magnetic coils. The basic design of a tokamak involves a toroidal, donut-shaped chamber surrounded by magnetic coils. A strong toroidal magnetic field is induced, and a poloidal magnetic field is also created within the plasma by a current flowing through it, known as the plasma current. The combination of these magnetic fields confines the plasma in a way that prevents it from touching the walls of the chamber, maintaining the high temperature and pressure required for fusion reactions to occur. Stellarators are another type of magnetic confinement device. Unlike tokamaks, stellarators have a more complex, non-axisymmetric magnetic field. This complexity is designed to confine the plasma without the need for a plasma current. The advantage of stellarators is that they don't rely on a plasma current, which simplifies the engineering and avoids certain instabilities associated with tokamaks. However, they are generally more challenging to build and operate. Now, we are proceeding to the system and key components of magnetic confinement. Firstly, the magnetic coils. Magnetic coils are fundamental components that generate the magnetic fields necessary for confining and controlling the plasma. The configuration of these coils is crucial, and in the case of stellarators or tokamaks, they create the toroidal or helical magnetic field required for plasma stability. The helical magnetic field has two components. 1. A toroidal component, which points the long way around the torus or a donut, and 2. A poloidal component directed the short way around the machine.
Secondly, plasma heating systems. Plasma heating systems provide the additional energy required to achieve and sustain the high temperatures needed for fusion reactions, since a plasma comprises charged particles, which is ions positive and electrons negative. Powerful magnetic fields can be used to isolate the plasma from the walls of the containment vessel, thus enabling the plasma to be heated to temperatures more than 100 million Kelvin. Plasma heating systems contribute to reaching and maintaining the temperatures essential for initiating and sustaining fusion reactions. Next, vacuum vessel. The vacuum vessel is a carefully designed chamber that houses the plasma and other components. It creates a low-pressure environment to facilitate the generation and maintenance of high-temperature plasma. The vacuum vessel ensures the appropriate conditions for fusion reactions by providing a controlled and low-density environment. Now, we move on to the technology of magnetic confinement. We are excited to share with you one of the most remarkable projects in the field of fusion energy, which uses one type of magnetic confinement, and that's the ITER project. ITER stands for the International Thermonuclear Experimental Reactor, and it's truly a global effort, involving 35 countries from around the world, including the European Union, the United States, Russia, China, India, Japan, and many others. The main goal of ITER is quite ambitious. It aims to demonstrate the feasibility of nuclear fusion as a large-scale and sustainable source of energy. This means achieving and demonstrating sustained nuclear fusion reactions, where we produce more energy than we put into the system. Essentially, it's a critical step toward developing practical and commercially viable fusion power plants. ITER utilizes a tokamak design, which is essentially a toroidal or donut-shaped magnetic confinement device. The tokamak design is known for its ability to confine high-temperature plasma over extended periods to generate the intense magnetic fields required for this. ITER employs advanced superconducting magnets. These magnets are cooled to extremely low temperatures to achieve superconductivity, allowing for the creation and maintenance of the necessary magnetic confinement. As of now, the construction of the ITER facility, located in Saint-Paul-les-Durance, France, is well underway. They've reached significant milestones in the assembly of the tokamak and other major components. In conclusion, ITER represents a major success in the field of magnetic confinement for fusion energy. As we move forward, the collaborative efforts of nations in projects like ITER bring us closer to the realization of practical fusion energy. Moving forward, let's delve into one of the most fascinating stellarator experiments in the world, Wendelstein 7X, often abbreviated as W7X, situated in Greifswald, Germany. W7X is a groundbreaking project that explores the potential of stellarators for achieving controlled nuclear fusion. W7X has a primary goal which is to investigate the suitability of the stellarator concept for future fusion power plants. Unlike the more common tokamak design, stellarators use a helical, twisted magnetic field to confine and control high-temperature plasma. The unique design of W7X aims to optimize plasma stability, confinement, and temperature. At the heart of W7X is its helical magnetic field. The twisted, three-dimensional coils create a magnetic configuration that provides inherent stability to the confined plasma. W7X employs an island diverter configuration, a design feature that enhances plasma performance and helps control plasma instabilities. Wendelstein 7X holds the distinction of being the world's largest stellarator experiment. Its size and advanced design make it a crucial player in the field of magnetic confinement research. In conclusion, Wendelstein 7X stands as a remarkable success in the realm of stellarator experiments. Its achievements in optimizing plasma performance and exploring the potential of helical magnetic confinement are paving the way for the future controlled nuclear fusion. W7X is a beacon of innovation and collaboration in our quest for sustainable and abundant energy.
Today, we've explored the captivating world of magnetic confinement for fusion energy, a field that holds the promise of clean, abundant power for our future. From the fundamental principles of nuclear fusion to the intricate designs of tokamaks and stellarators, we've delved into the heart of a transformative energy pursuit. The journey to practical fusion energy is a marathon, not a sprint. Challenges persist, but so does human ingenuity. Ongoing research, technological breakthroughs, and international collaborations underscore our collective determination to harness the power of the stars. In conclusion, magnetic confinement isn't just about containing plasma, it's about containing the potential to revolutionize our energy landscape. As we navigate this frontier, let's remain inspired by the idea that fusion energy isn't just a possibility, it's a future we're actively shaping. Before we end our topic for today, let's take a look at verse 12 from Surah An-Nahl in the Quran. And he has subjected for you the night and day, and the sun and moon, and the stars are subjected by his command. Indeed, in that are signs for a people who reason. This verse explains that the sun is created for the benefit of human beings. The sun is the largest object in our solar system, and the energy that comes from the sun to the earth is in two main forms: heat and light. In order to get the maximum amount of energy from the sun, we first have to understand how the sun shines, which is from the fusion reaction. Therefore, we have to be grateful for the existence of stars, which teaches us another way to produce energy from fusion reaction. That's the end of our topic for today. I hope you gained something from today's video. Thank you for watching. See you.